Today we want to review our strategy for approximating definite integrals based on the strategy that we assume the function is constant for small changes in x. In this case, like the case we had yesterday, the smallest delta x that we can set up is a delta x of 5 because the only data we have is at 5, 10, 15, and 20. So the only data we have is 5 units apart. So that's the small, that we can't say a delta x of 2 because we don't have information for what's going on at 2 or 4 or 6 or 8. So the smallest we can do is delta x equals 5. And that means the most rectangles we could use is 4. We usually call this n for number of rectangles. At most, we can make n equals 4 rectangles. So if our delta x is 5, what we have to do is assign a value for the function. We're going to make rectangles out of each of these intervals. So we have the width of 5. This is going to be our width. And our height is going to come from values for the function.
Is it just a GMAT contest?
And our height is going to come from f of x. So here are the strategies that we can use and the notations that we're going to use. So one thing we can do is say, well, the function starts off at 10 and ends up at 25. So 10 is, I can use the left endpoint of this interval and use that as the basis for the entire interval. So I'm going to use a left endpoint approximation with n equals 4 subintervals. So first let's start with the left endpoint approximation with 4 subintervals. We're going to have notation for this. We're going to abbreviate this by saying left and then in parentheses 4. Left endpoint approximation with 4 subintervals. So our delta x is 5. Our delta x is going to be 5. And our height is going to be the left endpoint of each of these 4 rectangles. So the first one will be 10 times the delta x of 5. The next one will be 25. The next rectangle is a 25 on the left and 35 on the right. So I use the left 25 times 5. Then the third one has 35 on the left and 40 on the right. So I'll have 35 and 5. And then the fourth rectangle has 40 on the left and 42 on the right. So I'll have 40 and 5, because we had previously decided to use the left endpoint as the value for the function. So if we calculate this, we'll have, I'm going to factor out the 5 and just go 10 plus 25 plus 35 plus the 40 times 5. Our total is 550. So one approximation, the left endpoint approximation is 550. Now when we make that approximation, I made the heights in green. I meant to make them in red or pink. When we make that approximation, we're imagining this rectangle, this rectangle, this rectangle, and this rectangle. We're imagining these 4 rectangles. So there we can visualize that. Here are these 4 rectangles. So let's shift over and do the right endpoint approximation. Once again, with n equal 4 subintervals. So we'll call that right 4. And now we'll use the right endpoint approximation. So in this first rectangle, we have 10 and 25, 10 on the left, 25 on the right. So we'll use the 25. So 25 times 5. Then the next rectangle is 25 on the left and 35 on the right, so we'll use 35 because we're using the right endpoint approximation. Then the third rectangle has 35 on the left and 40 on the right, so we'll use 40. Then the last one has 40 on the left and 42 on the right, so we'll use 42 times 5. And we'll just add all these up. So now we'll have 25, 35, 40, and 42 all multiplied by 5. So the right endpoint approximation is 710. So, oops, little angle there. Whatever this function is doing, we can say that the area under this curve, whatever it happens to be doing, is more than 550 and less than 710. It's got to be between these two values. Unless, of course, someone is saying, oh, bahaha, but between 0 and 5, it actually goes way up here and then comes back down. And then between 5 and 10, it actually goes negative. If this is the information you have, and in truth, this like drips down below the x-axis, then whoever's giving you the information is cheating, and that's not, and they're just not playing fair. So just say, fine, if that's the way you want to play this game, you just do you. I'll just take that loss of points and walk. What we're calculating in this case, we're taking this first interval from 0 to 5, and we're using the right endpoint. So we're calculating this rectangle. And then the second rectangle is up here. We're using that value for a height. And then the third one, we're using the 40 for the height. And then the fourth one, we're using 42 for the height. So this is going to be an overestimate of whatever's going on in the function. So we're calculating this area, and then this area, and this area. So the function, if the function is being continuous and we have a reasonable expectation that there's no weird outliers in these data points, not like some sign going up here, then we can reasonably expect the actual value of the definite integral to be between 550 and 710. Any questions? All right. So yesterday, since we have a value of the definite integral between 550 and 710, it raises the question, is it reasonable to find the average of those two? So it's important before you just start finding the average of two things, if it's reasonable to find the average of those two things. I think I've mentioned before that the average human being has one ovary and one testicle, and that is a very poor description of the average human being. So is it reasonable to find the average? And the answer is yes. So the average, and yesterday the subject of trapezoids came up. We're finding areas of trapezoids. The reason that it makes sense to use trapezoids is that if we take two rectangles, the average of those two areas is going to be the area of a trapezoid. I have a purple pen, so I have a blue and a red. So the average of two rectangles is going to form a trapezoid. So here is a trapezoidal area. So this is why it makes sense to find the average of those two rectangles. We're just finding the area of a trapezoid in between the left and right. And the area of a trapezoid is 1/2 base 1 plus base 2. It's the average of the two bases multiplied by the height. So that's why it makes sense to just average these two, because we're still trying to find area, and we're just finding the area of a trapezoid. And a trapezoid is the average of two rectangles. A trapezoid is the average of two rectangles. If we have one rectangle with a height of B1, with a base of B1, and another rectangle with a base of B2, and both have the same height, then the trapezoid, to get the area of the trapezoid, we just find the average of base 1 and base 2, multiply that by the height. Once we draw the trapezoids on which this average is based, we can see what assumption we're making when we find the average of the left and right endpoints. What we are doing is assuming that the function is linear on each subinterval. So when we find the average of the left and right approximations, we're using trapezoids to find the area, and we're assuming that the function is linear on each interval. So when we average the left and the right approximations, we're using trapezoids to find the area. And we're assuming that f of x is linear on each subinterval.
At the very bottom, can you get your screen? Oh, yeah, this one.
So when we average the left and right approximations, we are using trapezoids to find the area, and the base assumption changes from constant, f of x being constant for the subinterval, to being linear on each subinterval. We can summarize this with what we call the trapezoidal rule, but not on this piece of paper. We can summarize this using what we call the trapezoidal rule. And unsurprisingly, we use the abbreviation TRAP. TRAP n is the average of the left n and right n approximations. It only works if we're using the same number of subintervals. They have to be subintervals and not rectangles. Left and right have rectangles. So what we would be doing in this case is finding the area of each subinterval using a trapezoid. So if I have x and f of x, I'm going to reproduce the function here. 0, 10, 5, 25, 10, 35, 15, 40, and 20, 42. So if we look at the first trapezoid between 0 and 5, once again, our delta x, our height, is going to be 5 for all of them. For 4 trapezoids this time. So we're going to do trapezoids this time. So the first area, or the first interval, is going to have an average of 10 and 25. So the trap 4 approximation will be the average of 10 and 25 times the 5. The next trapezoid will be the average of 25 and 35 times the height, 5. The third trapezoid will be the average of 35 and 40 times the height. And the fourth trapezoid will be the average of 40 and 42 times the height. So rather than work this out, we could have found this by finding the average of 550 and 710. So we should, let's find out what we're going for. So we're taking 550 and 710 and dividing that by 2. So we're going for 630. Let's reorganize this a little bit, not by just adding things up. Don't just start adding things up like some kind of calculator. Let's break this down and see what's going on. First of all, let's factor out a 1/2, and let's factor out the delta x. So factor out the 5 for the delta x, and then the 1/2 from all 4 terms. Now let's look at what we have. We've got the first term, 10, the first entry, 10. We have 2 copies of a 25. So I'm going to say there's 110 plus 2 25s. Then we have 2 copies of 35. So plus 2 times 35. And we have 2 copies of 40 plus 2 40s. And only 1 42. So we can see what the pattern is. The 2 on the end only appear once. All the ones in the middle appear twice. Because 25 is the second height of the first rectangle and the first height of the second, trapezoid. It's the right end of the first trapezoid and the left end of the second trapezoid. So there's 2 25s. The 35 appears 2 times. The 40 appears 2 times because it's in the one on the left and one on the right, but now 42 we're at the end, so it only appears once. The first and last ones only appear once. The first and last ones only appear once. The values in the middle appear twice. So that will help us summarize this trapezoidal rule. let's make sure that this is going to give us what we want. So 5 over 2, factor out the 5, factor out the 1/2 from doing the averages. I have 110, 2 25s, 2 30s, 2 40s, and 1 42. Just like we suspected. Any questions? So it's also the average of the left and right approximations. So also trap 4 is the average of the 550 and the 710, which is also 630.
I'm at 30.
Any questions?
No, there's 40.
Do you have a preference if you ask us to show our work, which one we use?
No. If I previously had asked you to do left and right, then just find the average. If I just lead with you finding the trapezoidal rule, it's probably faster to do this. I'm not sure. I haven't broken down exactly how many calculations are involved in each one. So whichever one occurs to you to do, or if you've already got left and right, then doing this would be crazy. Just average the left and right. So as usual, whatever is most convenient. Any other questions? Great, let's pause the video here and look at some other approximations.